Riemann sums and finding the area under a curve using geometry was an excellent introduction into Calculus 2. But to really get into the meat of Calculus 2, we need to start talking about antiderivatives. An antiderivative is exactly what it sounds like. It's the opposite of the derivative. It's like undoing the derivative. Just like multiplication and division undo each other, addition and subtraction undo each other, natural log and e undo each other, antiderivatives and derivatives undo each other. So 5.3 sounds really intimidating. The fundamental theorem of calculus. That sounds pretty scary. It's not so bad. So let's take a look at the integral that we're looking at. We remember integral means area under the curve. So this fundamental theorem of calculus tells us that if we take the integral from any point to any x value of f of t dt, if I take the derivative of that, all that's going to happen is that my derivative and my integral will cancel each other out. And I'm going to get f of x, my original function, back. So the antiderivative, the derivative of the antiderivative is just the original function. The reason this is the fundamental theorem of calculus is because it lets us go back and forth easily between derivatives and antiderivatives. Let's take a look at example 1, which is on page 406, and it tells me to take the derivative from 0 to x of the integral t plus 1 dt. So to take the derivative of the integral, or the derivative of the antiderivative, I just get my original function with respect to x. So as long as I'm going to just a constant here, I have no problems, nothing to worry about. But when I take a look at the next one, in example 2, I have a little bit more of an issue. Now in example 2, I'm being asked to do something a little bit more difficult. I'm going from, or a little more complicated. I'm asked to take the derivative, the dx, of the integral 3x to the 3x squared plus 1 of the square root of e to the t plus t dt. So I really need to account for that 3x squared plus 1. And what I'm going to do first is just a u substitution. I'm going to replace that with u. So let's call u 3x squared plus 1. All right, so now I have d du of the integral from 4 to u, the square root of e to the t plus t dt. So when I take that, I'm going to get e to the u plus u times, I can't forget, du dx. Because I need to still figure out how to put that into my x value. So let's find du dx. So du dx is 6x. So now this is going to become e to the 3x squared plus 1 plus 3x squared plus 1 times 6x. This is just like doing the chain rule for something a little bit more complicated. So it's kind of the chain rule for the integral. So in example 3, I'm asked to do the derivative of the integral from x cubed to 5 of t to the 4th plus 1 to the 1/3. So there's a couple things I need to do for this one. First, I need the 5 to be on the bottom of my integral. And hopefully you remember from last unit, they gave us some random things that we needed to know about integrals. And one of them was if you flip over the integrands, so if I make it from 5 to x cubed, I just add a negative sign out in front. All right, now this is looking a little bit better to deal with. It's not perfect, but it's looking a little bit better. Now I'm going to have to use my u substitution. So let's let my u be x cubed, and then my du dx is 3x squared. So now I have d du, the integral, the negative integral from 5 to u of t to the 4th plus 1 to the 1/3 dt. And this whole thing is going to be times du dx to take care of that chain rule part. Okay, so now let's do the antiderivative of the derivative here, and we're going to have the negative is going to just come for the ride. So I'm going to put that on the outside. U to the fourth plus 1 to the 1/3 times du dx. All right, now let's substitute in what I know for u. U is x cubed, so let's substitute that in. So we have negative x cubed plus 1 to the 1/3, and then times du dx is 3x squared. So if I wanted to make it look a little bit prettier, I could move it out in front. Negative 3x squared times x cubed plus 1 to the 1/3. So now we're at the second part of the fundamental theorem of calculus. This is the one we use more often. The other one kind of lets us do stuff, but this one is used all the time. And whenever we have limits or bounds on our integral, we will always, when we take the antiderivative, use those bounds using the second fundamental theorem of calculus. So what that tells me is, first I'm going to take the antiderivative of f of x dx, and I get f of x. Then I'm going to evaluate it with respect to a and b. And the way I do that is f of b minus f of a. So let's draw like a little picture of what's going on. I know we haven't talked about this in a while, but let's say there's a and there's b. So let's say that this is what my picture is going to look like. Remember, the integral is the area under the curve. So if I'm finding the area under the curve with respect to b, which is this one, that's all of that. Then if I'm finding the area under the curve with respect to a, that's all of this piece. So if I take away the part with respect to a from the part with respect to b, I'm left with just the inside between a and b. And that's what this integral is asking me for. What's the area under the curve between the two of them? So hopefully that picture was illustrative. All right, let's do a couple of examples all about this. We're on example 4 on 5.3. So it's 1/3 x cubed is my antiderivative, and now I don't need to worry about a plus c because that constant's going to get canceled when I do my subtraction. So I need to evaluate it from -2 to 1. So I plug in the top number first, 1/3 times 1 cubed minus, I subtract the bottom number, -2 cubed. So that's 1/3 minus, it's -8/3. So that'll be plus 8/3, so that's 9/3, or 3. So the area under the curve between 1 and -2 for x squared, so that looks like this. If I go from -2 to +1, this area under the curve is going to be 9. It's going to be 9/3 or 3. So for the antiderivative of cosine, for part B, the antiderivative of cosine is going to be sine. Because sine of x, the derivative is cosine, I go from 0 to pi/6. So we're looking at, something that looks like that, and we want to go and figure out that amount of space between 0 and pi/6. So I need the sine of pi/6 minus the sine of 0. Sine of pi/6 is 1/2, and the sine of 0 is 0, so the area under this curve is 1/2. I think to do the next two, I'm just going to get another page. So this one asks us to find the integral, or the area under the curve, between 0 and 3/2 of 1 over the square root of x squared dx. Now hopefully this rings a bell. Hopefully you know that you've seen that before, and hopefully you're saying, like, I know that's one of those special ones that I was supposed to remember. Well, it's arc sine. So it's sine to the -1 of x from 0 to √3/2. So the sine to the -1, √3/2 minus sine to the -1 of 0. So we're undoing sine. We're looking at what gets us √3/2 as a y value on the unit circle, and it's pi/3. And what gets a sign of 0 is also 0. So pi over 3 minus 0. The area under this curve is pi over 3. In D, hopefully you also see a function that you remember. So this is asking us to find the integral of the area under the curve between 1 and 2 of 1 over x dx. And hopefully 1 over x is something that you know. It's the natural log of the absolute value of x from 1 to 2. This is kind of a small piece, but it's important. When we take the antiderivative of natural log, we always have the absolute value symbol. When we do the derivative, we don't need the absolute value symbol. But for the antiderivative, we need the absolute value symbol. So it's the natural log absolute value of 2 minus the absolute value of 1. And hopefully you remember that the natural log of 1 is just 0. So this is the natural log of 2. Let's take a look at another example. Example 5 asks us to find the area under the curve from of e to the x from negative 1 to 1. So the first thing I'm going to do, I'm going to sketch what it's actually asking me to do. E to the x looks something like that. We're going to go from negative 1 to positive 1, and we're going to figure out this area. So it wants me to find the integral from negative 1 to positive 1 of e to the x dx. The antiderivative of e to the x is the same as the derivative of e to the x, is just e to the x. We're going to evaluate that between negative 1 and positive 1. So that's e to the 1 minus e to the negative 1. There's a bunch of ways I can write this. I can write this as e minus 1 over e. And if I need to make a common denominator, I could. I don't have to, but if it asked me to, if it was a multiple choice question, that would be e squared over e minus 1 over e squared minus 1 over e. Let's look at an application problem. The population of the United States is growing at a rate of p prime of x is 2.867 times 1.09 to the t million people per year, where t is the number of years since 2015. It wants us to find the area under the curve between 0 and 5 of p prime of t dt. So let's start by writing that antiderivative. So we're going to go from 0 to 5, 2.867, 1.009 t dt. So we need to recall that the antiderivative of a to the t is a to the t over ln a. And the way that I remember this is the derivative, so this is the antiderivative, but the derivative of a to the t is a to the t ln a. So if I take the antiderivative, I'm missing this ln a, so I need to divide by it. Okay, so the 2.867 is just going to come for the ride. I'm not even going to worry about it. So it's going to be 2.867 and then 1.009 t to the t over ln of 1.009. And that's all evaluated between 0 and 5. Let's plug those in. We have 2.867 and then 1.009 to the 5th, all over ln 1.009 minus 1.009 to the 0, all over ln 1.009. Now I can just plug that into my calculator exactly as I see it without doing any other work, and I'm going to get 14.661. Now let's see what that's actually asking us to do, or what that actually means. The next one says to interpret the integral from 0 to 5 of p of t dt in the context of the problem. Let's read the problem again. The population is growing at a rate of, and they gave us the rate, million people per year, where t is the number of years since 2015. So if we're going from 0 to 5 years, that means that we're going between 2015 and 2020. And overall, the population has grown $14.661 million people. Now, this is a really important, part C is really important. We haven't done a part C yet, but it's very important. It's telling us that the population was 320 million people in 2015. What will it be in 2020? So this is a really important equation that we're going to write. The population of in 5 years is equal to the population at year 0 plus that integral that we found. So we're going to have 320 plus the 14.661. So overall, we're going to get 334.661 million people. This is really important. I know I just kind of glossed over it, but we're going to do many more of these. And this is very often an open response question where you have to find the initial, they give you the initial, and you have to find the end result total. So you take the change, add it to what they gave you to begin with, and then you have your total.